Hey students, in today's session, I'm going to talk about finding the center of mass by bypassing integration. Now, this video is for all those students who have studied this chapter already, because you will be able to understand better only when you have seen an exposure to the topic of center of mass. If you haven't done that, then you probably won't be getting this video. You'll not be able to understand. So this is a prerequisite for this video, is that you have completed your center of mass either in school or in a JE batch. Okay, so let's get started. So I'll start by mentioning things that you ought to know by now, given that you have studied this chapter. Then I will tell you things that you probably don't know, and then we'll see how I can make you understand those things that you don't know. So let me start by writing what you already know. Okay, so, or what you ought to know. Okay, so what you should know right now is the definition of center of mass. Like, what exactly is center of mass? So in a very crude language, we can say that it is the point where the entire mass of the object can be assumed to be concentrated for the purpose of calculating the gravitational force, we can say. Okay, technically we say that it is a point about which the sum of mass moments of the of all the particles of the system is zero. Okay, so that is how we define it. Again, I'm not going to specifics, otherwise the length of this session will go very long. The formula, I'll just write the formula so that you can recognize what I'm talking about. The formula to find out the location of center of mass was m1 r1, okay, plus m2 r2, and so on, like whatever number of particles you have, and then you divide it with the total mass. Let me write total mass as m. So m indicates m1 plus m2 plus m3 and so on. Now this was the formula when you have discrete particles, separate particles present in at various points in space, and just in case you have a continuous mass distribution, that means you have a body. In that case, you are supposed to write dm into r vector integration of this divided by integration of dm. So these are the formula with which you can locate the center of mass. Okay, now this is something that you should be knowing. What else you would be knowing is that if an object possesses an element of symmetry, then the center of mass lies on the object. For example, if we construct alphabet A by using a uniform wire, okay, like this, so we are in a position to declare that the center of mass of this A will lie on this line, because this plane is the plane of symmetry. So the center of mass needs to lie in this. Okay, similarly we can talk about other objects. If you need some more examples, then alphabet B will also have an element of symmetry, so the center of mass of alphabet B needs to lie on this line. Okay, so with objects that possesses one element of symmetry, we can say that the center of mass should lie on it. What if an object possesses more than one element of symmetry? For example, let's say if we talk about a uniform rectangular plate. Okay, so if we talk about a uniform rectangular plate, now I hope you all can see that it possesses two elements of symmetry. One is this plane and the other is this plane, and the center of mass needs to lie on both of them, and therefore it is mandatory that the center of mass has to lie at the intersection of this. So this is the center of mass. So using this principle, we are able to locate the center of mass of majority of the objects with regular geometry, and if they are uniform. For example, I'm talking about a uniform ring. We know where the center of mass would be. A uniform disc, a uniform hollow cylinder, a uniform solid cylinder, a hollow sphere, a solid sphere. So for all these entities, we can very easily find out the center of mass just by using principles of symmetry. Okay, so again, this is something that you should know. You ought to know this. What else you ought to know? I'm pretty sure that wherever you have studied about the center of mass chapter, whether it's your JE batch or whether it's your school curriculum, you would have learned about the location of center of mass of half regular objects. So if I talk about a uniform half ring, okay, uniform half ring, I think, okay, and it should be like that only, okay, that the center of mass of a uniform half ring, I think you know where it is. It will lie on the element of symmetry, which is which is this line. So we know that it would lie on this line. And where will it lie on this line? So this is something that we discover from integration, that this distance would be 2r by pi. So you learned this by integration methods. Okay, so this result you should be knowing it by now. If not, then the reason is either you have not studied this chapter. So when you study this chapter, you will come to know about this, and your teacher will most likely derive it using integration. And if your teacher has taught this already and you don't know it yet, that's probably because you are not diligent enough. You need to pull up your socks. You need to do better than that, student. Okay, this is uniform half ring. Similarly, we can talk about a uniform half disk. So let me do it here. We can talk about a uniform half disk. Remember, guys, all of this is what I expect you to know. I want to start from a place where you guys are comfortable. So I'm first putting it out that what are the things that you ought to know at this point. And in this, then I will teach you that what you most likely don't know. So this would be the element of symmetry and the center of mass. Okay, if you know this, you know, this is at a distance of 4r by 3 pi. For a uniform half disk, it is at a distance of 4r by 3 pi. Okay, again, this is something that your teacher would have derived by using integration, or they may have just told you the formula. They may not have derived it. That is also one of the possibility, which is fine, you know. You will do the derivation yourself when you study calculus. When you learn to integrate, you will be able to derive it yourself. Okay, so next we can talk about uniform hollow hemisphere. Okay, we can talk about a uniform hollow hemisphere. Okay, uniform hollow hemisphere. So for a uniform hollow hemisphere, okay, this doesn't look very good. Okay, so for a uniform hollow hemisphere, the center of mass, okay, again will lie on this axis, on this line. Okay, okay, and where will it lie? So it would be at a distance of r by 2 from the center. Okay, we can also talk about a uniform solid hemisphere. We can talk about a uniform. Again, guys, this is all something that you already know. Okay, I'll come to the point what you don't know. Okay, just to make my lecture complete, I'm writing all these things. So uniform solid hemisphere. Okay, where will the center of mass of this will lie? Again, this would be the symmetry axis. So center of mass lies at a distance. It lies at a distance of 3r by 8. Okay, it lies at a distance of 3r by 8. Okay, so we have talked about a half ring, half disk, hollow sphere, hollow hemisphere, solid hemisphere. What next we can talk about is a hollow cone, uniform hollow cone. Okay, so for a uniform hollow cone, the location of center of mass is at h by 3. If this is the height, then the center of mass is at a distance of h by 3 from the base. What is important here to note is that this location is not dependent on the radius of the hollow cone. Okay, and if we talk about a solid cone, if we talk about a uniform solid cone, okay, if I talk about a uniform solid cone, then okay, the uniform solid cone is the location of center of mass is at a height of, again, this is height h, so it is at a height of h by 4. Okay, so these are some of the results that we already know. Okay, another result, what about the location of center of mass of a triangular plate? Okay, so if we want to talk about a uniform triangular plate, okay, so for a uniform triangular plate, okay, the centroid becomes the center of mass. Okay, all right, so these are the results that you already know. Now you would also know that most of these results are derived using integration. Now my question is, can we bypass integration? Now the answer is yes, we can definitely bypass integration. Uh, let's see how to do that. We can bypass integration and find at least some of these results, and you would be blown away to see. So this is something that you know. Now I'll come to the next part of my presentation, and I'll talk about what you possibly don't know. You may know it, the likelihood is less. Okay, you may know it, but the likelihood is less. So what you possibly don't know. Okay, so let me talk about a theorem which is called Pappus theorem. Okay, and actually there are two theorems. Okay, one for the curves. Okay, one for the curves and the other for area. Okay, so I'll explain you both, and this can be used to find out center of mass of curve and of area. Okay, both belonging to a plane. And then there are some techniques. Okay, there are some techniques that you can use to get the center of mass. Okay, so let me start now. So guys, from here we start the business end of this session. So I am now telling you things that you probably don't know. Okay, so what is Pappus theorem for a curve? Okay, so let me first explain this. Okay, Pappus theorem for a curve. Now let me explain this. So first of all, what are the points to remember? That this curve, you know, we are dealing with a planar curve. That means our curve needs to belong to a plane. You know, you can make a curve which is three-dimensional in nature. You know, I can, if I move my finger like this, so the trajectory or the tip of my finger has traced. It's a curve, but it's not in a plane. Okay, a very simple example would be the shape of a spring. That's a curve, but that is not a plane. So we are dealing with a planar curve. Okay, so let me just draw a random example. So let's say this is a planar curve. Okay, now I want to know where the center of mass of this curve is. You know, this mass is distributed on this curve, and just in case you are thinking that if we can make it straight, then this point would be the center of mass. No guys, that logic doesn't work. You know, it depends on the shape. It depends on the shape. For example, if if we go by that logic, so for a semicircle also it would be very easy for us to declare that the center of mass would be the midpoint of that, you know, wire if we make it straight, but that is not the case. It depends on the shape. So the center of mass should lie somewhere here, but we want to locate it. Okay, so what do we need to do? So this theorem involves a planar curve. What else does it involve? It involves an axis in the plane of the curve, not intersecting with the curve. So it involves non-intersecting axis in same plane. So you need to choose one. Okay, you need to choose. So this is your choice. You just have to ensure that it is not intersecting with the curve. Okay, so you have to choose this. So let's just say that I chose an axis like this. Okay, I chose an axis like this. Now next what you have to do, you have to create a surface of revolution around the axis. What does that mean? So suppose you tie threads here. Again, you have to imagine this. Suppose you tie threads here and threads here, and then you move this curve around the axis, keeping the threads taut always, keeping them taut always. Okay, then can you tell me that what kind of trajectory these points will trace? Like this will trace a circle, even this will trace a circle, and all other points will also trace a circle, giving us a surface of revolution. Yes or no, everyone? It will give us a surface of revolution. Like this point will go in a circle like this point will go in a circle like this point will go in a circle like this, and so on. So what you will end up would be like a vase shaped surface, vase, flower vase. Okay, so this is called the surface of revolution. Okay, so it involves a planar curve, it involves a non-intersecting axis. Then you have to generate the surface of revolution. Okay, the next step is that you generate surface of revolution. Now what does this theorem say? This theorem says that if the area of the surface of revolution, A is the area of surface of revolution. Okay, if L is the length of curve, if L is the length of curve, if R is distance of CM from axis, CM of curve, okay, from axis, then A is equals to L into distance covered by COM in one revolution, okay, which transforms to A is equals to L into 2 pi small r. Yes or no? A into 2 pi small r, because the center of mass also went in a circle of radius r. So the distance covered by the center of mass will be equal to the circumference. So this is Pappus theorem, and it will help us to determine the center of mass, let's say of a semicircle. We can do that. Okay, so let me show you how we can use this theorem. So this theorem is generally valid provided we should be able to use it. For example, if I'm generating a surface of revolution and if I don't know the area of that surface, this area, okay, if I don't know the area, okay, this area, then although the theorem is applicable, but I am incapable of making use of this because I don't know the value of A. So the surface of revolution that we are generating, we should be able to write the area of that surface to be able to use this method. Okay, let me demonstrate how we can use this. So I'll give you an example. Okay, I'll give you an example. We are going to use Pappus theorem to locate, that means to find, okay, COM of a uniform semicircle. Okay, now the first thing is that is a semicircle a planar curve? Is it a curve belonging to a plane? I think you guys will agree with me. And so the first condition is satisfied. It is a curve belonging to a plane. Next thing, do I have to choose an axis that is not intersecting with this curve, but it should belong to this plane, and it should be a convenient axis. What do you think, guys? What is the axis that we should choose? If you ask me, what comes to my mind is an axis like this. Now you will say, sir, it is intersecting. No, it is not intersecting. It is infinitesimally close to the two ends, but it is not intersecting. And it is up to me how close I want to keep this axis. So I'm keeping it infinitesimally close, but it is not intersecting. Okay. Now, if I think about the surface of revolution, okay, let's do one more point. I don't know where the center of mass is, but I'm very sure that it will lie on the line of symmetry. So it should be somewhere here. So this is the distance r that I am trying to find out. And let's say capital R is the radius of the uniform semicircle. Okay. Now, when I rotate it, are you able to think of the shape of the surface of revolution that we will get? Okay, so the shape that you will get will be a sphere. Okay, a sphere of radius capital R. So do we know how to write the area of a sphere of radius of capital R? So definitely we know that the area would be 4 pi r square. Okay. Do we know the length of this curve? Of course we do. It is pi into capital R. And then we have to multiply this with 2 pi r. This is what we said, right? This is what we said. We'll go back. So area is equals to length into 2 pi r. So that's what I've done here. I know the area, I know the length of the curve. I've multiplied with 2 pi r. Now you do the math. I'll do the math. Okay, so what is happening here? So what all things are getting cancelled? So this 2 pi and this 4 pi gets cancelled to make a 2. Then one of the r gets cancelled. So small r is nothing but 2r by pi, and voila, we have obtained the result without integration. Of course, we made use of this Pappus theorem. So, but there are techniques also, even without using Pappus theorem, we will be able to derive certain results. So this is what we have done. This is what we have achieved. Now, this was an example of using Pappus theorem for a curve. Let's also talk about Pappus theorem for a area. Let's see what it says. Okay, so what it says. So next is that we are going to discuss. What it says. So, next is that we are going to discuss. What it says. So, next is that we are going to discuss. What it says. So, next is that we are going to discuss. What it says. So, next is that we are going to discuss. What it says. So, next is that we are going to discuss. What it says. So, next is that we are going to discuss. What it says. So, next is that we are going to discuss. What it says. So, next is that we are going to discuss. What it says. So, next is that we are going to discuss. What it says. So, next is that we are going to discuss. What it says. So, next is that we are going to discuss. What it says. So, next is that we are going to discuss. What it says. So, next is that we are going to discuss. What it says. So, next is that we are going to discuss. What it says. So, next is that we are going to discuss. What it says. So, next is that we are going to discuss. What it says. So, next is that we are going to discuss. What it says. So, next is that we are going to discuss. What it says. So, next is that Pappus theorem for an area. Okay, again, it is very similar to what we just did. Okay, just that now instead of a curve, we are going to need a planar area. So we need a planar surface. Okay, we need a planar surface. We need to choose an axis, a non-intersecting axis. Okay, similar to the what we did in the previous case. We need a non-intersecting axis. Okay, in same plane. Again, we have to choose this. Okay, we have to choose this, and then we need to obtain the volume of revolution. Okay, we need to obtain. So I'll just demonstrate it. Okay, so let's talk about an area first. So let's say this area is the rectangle. So rectangle is definitely a planar area. Okay, so I've chosen this rectangle. Now I have to choose an axis. Okay, so let's choose an easy one. So you can choose an axis which is like this, which is very close, which is very close to one of the sides of the rectangle. Okay, again, infinitesimally close. Now you rotate this rectangle, okay, to give a complete rotation. And what do you think, guys? What kind of volume we are going to get? Think of it. So if you rotate this, plate, are you going to end up with a cylinder? Are you going to end up with a cylinder? Okay, so we will generate a volume of revolution. Now, what does this theorem says? This theorem says that if V is the volume of revolution that you will get, if A is the area of the surface, okay, and if R is the distance of center of mass of surface from axis, okay, then very similar, V will be equal to A into distance traveled by com in one revolution, which will turn out to be A into 2 pi r. So this is Pappus theorem for a curve. Okay, let's see an example. So we are going to obtain the location of center of mass of a half disk. Let's do for a half disk. Okay, so example, uniform half disk. Okay, so let's talk about a uniform half disk. So let's say this is a uniform half disk. This is our surface. Okay, let's say the radius of this is capital R, and I don't know where the center of mass is, but it will belong on this line. So it may be somewhere here at a distance small r. Now I have to choose an axis. So let's choose an axis. Which axis will you choose, everyone? Will you choose an axis like this? And if you rotate this surface about this axis, okay, if you give it up one complete rotation, then what kind of volume will you think you will generate? Are you thinking about a sphere? Because if you are, then you are right. It will generate a sphere of radius r. So the volume would be 4 by 3 pi r cube. Okay, the area is pi r square by 2, and we then write 2 pi r here. And let's do the math. Let's cancel out things that are getting cancelled. So this 2 pi goes with this, and we are left with a 2. Okay, then this r square goes, and now you can see that small r is nothing but 2 into 2, it's 4 r by 3 pi, and again we obtained the result of a disk without integration. Without integration. So this is how we can make use of the Pappus theorem. All right, now if we have understood this, let's see some other techniques as well. Let's leave Pappus theorem here. Let's learn some other techniques where we can see how to find center of mass without using integration. So let's talk about some other techniques. Okay, so let's start with a uniform triangle. Okay, uniform triangle. So we know that the center of mass of any triangle, it need not be a special triangle, but if we have a triangular plate, then the center of mass is the centroid of the triangle. How can we prove it? Okay, so to prove it, think about this, guys. What if I divide this plate into a number of strips like this, and think about what happens when you increase this number. You know, right now I've made probably 8 or 9 strip. What if you make 100 strip, 1000 strip, 10,000 strip? So can I say that each strip takes the shape of a rod or a wire? All right, so if I replace each strip with a particle of the same mass as that of a strip. So if this strip is of mass m1, if this is of mass m2, m3, m4, then technically what I can do, I can replace these strips with particles of these masses, and these masses will be present at the respective center of mass. So m1 mass will be present at the midpoint of this, m2 mass will be present at the midpoint of this, m3, m4, and so on. And when you do this, the collection you will get as a median. So we can say that this triangle can be replaced by a system of particles, and those system of particles will make a straight line, and that straight line will be the median of the triangle. Now, if we are able to prove that the center of mass will lie on this medium, and this median is no special median, it is a general median. So by the same logic, you know, by taking the strips like this, by taking the strips in a different manner, you know, like this, we should be able to prove that the center of mass must lie on another median, okay, which passes through this. So it should lie on this median as well, and therefore we will be able to prove that it has to lie on the centroid of the triangle. So we are able to prove that the center of mass of a triangle lies at the centroid without using integration. So that is one thing. Okay, let me show you another technique. So now that we know where the center of mass of a triangle lies, okay, let's see how we can use this information. Okay, so let's again talk about a uniform half disk. Okay, let's talk about a uniform half disk. So suppose we have a uniform half disk. Think about this, guys. Can I divide this disk into a number of sectors? Okay, and what happens if I keep on increasing the count of sectors? You know, think about 100, 200, 1000 sectors. So each sector changes into a triangle, yes or no? Each sector changes into a triangle. The more number of sectors you make, the closer to a triangle it becomes. And we can actually break this into identical triangles, and then each triangle can be replaced by a mass, by a particle of same mass, and we have to put that mass at the centroid of the triangle, because whenever we replace an object with a particle, what we do is that we put the particle at the location of the center of mass of the object. So when I replace this triangle, I need to put a particle at the center of mass of this triangle. So that would be somewhere here, and that would be like, if this distance is r, okay, if this distance is r, then the centroid of the triangle, we know that it is at 2 by 3 so of height. So this distance would be 2 by 3. So this distance would be 2r by 3. And similarly, this triangle. So you keep on replacing each triangle with particles present at their respective center of masses, and what you end up with is a semicircle of radius r, where r is 2r by 3. And now, guys, if I want to replace this semicircle with a particle, where should I put that particle? So I will have to put that particle at the center of mass of the semicircle, which is somewhere here. And this distance, you know, let's call it as x for now. So this distance x should be 2 small r by pi, and small r is what? 2r by 3. So 2 by pi into 2r by 3, and you see we end up with 4r by 3 pi. No integration involved. We just use the concept of triangles to get the location of center of mass of a uniform half disk. Can we do it with a uniform hollow cone also? Let's try this out, everyone. So if I think of a uniform hollow cone, okay, so can I break this uniform hollow cone into, again, many triangles? You know, if I can break the surface, think about this triangle, and I can think about many such triangles. Okay, so the collection of these triangles on the surface of the cone will turn it into a cone. Okay, so again the same logic, guys. Now I think you should be able to do it yourself. I will replace this triangle with a particle located here, and again here, 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 then here, 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 and we will end up with a ring. We will end up with a ring. If this slant length is L, then we will end up with a ring, the distance of which from the apex will be 2L by 3. Okay, the distance of which from the apex will be 2L by 3, and then the center of mass of this ring, okay, would be at the center of the ring here. Okay, so if this total height was h, okay, then this height will be 2h by 3. So we have located the center of mass of the ring, which was actually a collection of triangles. So in effect, we have located the center of mass of this cone at a height of h by 3. So we proved this result also without using any integration. So guys, I think we'll stop here today. So I hope you enjoyed this lesson, guys. So these are the kind of things that I'm going to teach in the Dhruv NSEP batch. And if you want to learn them all, then you should join this batch. Join this batch and learn these amazing techniques and tricks that are generally not taught in your regular classes. So I'll see you in the batch, everyone. Take care. Bye-bye.